This is project 1, video number 2, the one in which we read up the code. So I've fired up MATLAB already. I'll go to the editor, click it on Edit, and then I'm going to look at my old pencil and paper work. So I'm supposed to get started by initializing the constants, and this thing takes the three variables, mass, charge, and initial velocity in that order. So mass, charge, and initial velocity. Let's make sure I got that right. Namely the mass of the moving particle, the charge of the moving particle, and the initial speed. Yeah, mass, charge, and initial velocity. So get over to the editor. I go function. I'm making 3 graphs. I'll call it motion graphs. It doesn't return anything. I'm going to call that dummy. So my return variable I'll call dummy. Function name motion graphs. And was mass. Make it 0.002 kilograms. Charge, I'll go 1.5 times 10 to the minus 6. And initial velocity, let's say 100 meters per second, moving forward in the plus x direction. I'll put an end here. I'm going to right click on this, see if it tells me why it's got that underlined. I think we're fine. It is unset, so it's got no value. We're not going to use it. So I'm going to go over here and start initializing variables. K, the Coulomb constant, is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Let's see what else I needed there. Q1, the charge of the victim, 2.5 times 10 to the minus 9 is 2.5 microcoulombs. X1 and Y1, 0.1 and 0.01 meters respectively. So Q of the victim, I forget what I call that, Q1. I think I want to try to be consistent with this. I did call it. Oh, Q1, that's not the charge of the victim, that's the fixed charge. The user provides the charge of the victim. So Q1, Q2, Q3, Q4, they're each equal to 2.5 times 10 to the minus 6 coulombs. I just don't need them all. So I'm calling that one Q1. My name makes sense now. 2.5 E minus 6. That's how many coulombs it is. And X1 and Y1. X1 equals 0.1 meters, it's 10 centimeters, and Y1, it's 1 centimeter from the x-axis of 0.01 meters. Alright, and what did I say I was going to do? Accept those argument values, so we'll consider those to be known now. M, QP, and V0. Let's make sure. I made up numbers for them, but that's not my job. M, that's the user's job. QP, charge of the particle. I don't know if I want to look here, see if I use a capital P. Q sub P. I'll just use, I'm going to use capital P because I think of that as the point designator, designating a particular point, and then V0. Alright, that's more like it. Up here I need arguments. So QP might be unused. Yeah, it's unused, but we will fix that. Dummy I think will never get fixed. That'll probably always be underlined. This one might be unused. It's true, we haven't done anything with it. Alright, so the editor is giving us some warnings. Then set n is equal to 1. T of Tn is equal to 0. So that'll be T1, set T1 is equal to 0, x1 is equal to 0. I'm probably getting too far. Just set n is equal to 1 for now. And n equals 1. So T of n, I'm creating an array, and the nth element of it is going to be assigned the value 0. N is equal to 1, so what I'm saying is the first element of the array T, this like a bunch of values one after the other, is 0. X of n is equal to 0. A of n equals, and I think that's what comes up next, and it's a big expression. So 4kqq xn minus x1. Alright, keep in mind, yeah, this was x1, the position of the fixed charge. N can take on any value, 1, 2, 3, 4, 5, but when it's n is equal to 1, so that makes that also x1. That x1 represents a different symbol than that. So probably should have distinguished it when I was writing this up, having a different name for it, but on here it's easy to do that. It's kind of automatic. So it was 4 times, I need the times symbol, which is a star here, k times q1 times qp, and then times x n, it means the nth element of the array x, minus x1. So when n is equal to 1, as we have now, that's x and then open parentheses 1, close parentheses, where this x1 is just x1. This is the position of the fixed charge particle, and this is the position of the positions. It's going to be an array of values, the positions of the moving charge particle, the free one. And right now, when n is equal to 1, that position is 0. Alright. So QP, I think I need a times there, and I do want open parentheses, and then close parentheses over there, so that's actually good so far. And then divided by, I think, is what comes next. Yeah, the quantity m times that to the 3/2. Divided by, I'll go ahead and put that, m times, I think it's x of n minus x1 squared. And I think I'll bunch that up a little bit. This is just for the human reader here, this part. But that quantity squared. And I think I need another set of parentheses. I'll have that one with some extra spacing. Plus y1 squared. And that ends the thing that I'm raising to the 3/2. I'll go to the power of 1.5. And then this one is, to pair with this one, to say all this stuff is in the denominator. So in the denominator, I think I need the times. I definitely need a times. In the denominator, I've got the product of the mass and this quantity raised to the 3/2. Let's see if that's what I'm supposed to have there. Product of the mass, and then this entire quantity raised to the 3/2. So I think that looks good. Alright. But a little, on the getting started with MATLAB, we had this stuff that was done on an element by element basis. And here we're not working on a whole array, it's just like the nth element of this array, so we're only calculating a single value anyway and assigning it to a single value of an acceleration array. So we're okay, we don't have to worry about that. And then the nth value of velocity, well, the first value of velocity is v0, whatever the user tells us it is. So that should take care of it. Let's see if here it is. Over here, v is equal to v0. Okay, then we have to do this while loop. While xn is greater than or equal to 0, but less than or equal to 0.2 meters. Do all this stuff. So let's see if we can type in a while loop here. While x of n less than or equal to, no, greater than or equal to 0, and the double ampersand, x of n less than or equal to 0.2. Do all this stuff, and I'll type in an end for the end of the while loop, and here the stuff that it's got to do. So it's got to say t of n, so t sub n in my notes on the pencil and paper part is n times delta t. I'll just call it dt. And I haven't created a dt yet, so let's put dt equals 0.001, and that is something that I expect to have to play with. Probably have to reduce it. We'll see what the results look like. And then I think that's wrong. N is equal to n plus 1. So I bump up n by 1. then this is going to be n minus 1. Since n starts at 1 rather than at 0, because I can't store something in t of 0, the 0th element of an array isn't something that exists in MATLAB. That it starts with the first element of the array, so n has to start at 1. That means, like, when I get to the second one, I'm talking about the first time element, talking about the first time step. I'll use n minus 1. That gives me 1 when n is equal to 2 times dt. My first time step past times 0 is time 0.001 seconds. And then the next one would be 0.002 seconds, etc. So when n is equal to 3, that would give me a 2 there. So that's going to work. Then I'll try to look up here to see what comes next. X, I think, is the next thing I gotta calculate. So that's equal to the old x, the previous x, x of n minus 1 is what I'm writing there for the n minus 1 element of the array x, plus, I'm going to use the old velocity times dt. So the change in position is just the speed times the time, instead of velocity times the time. And then a of n, if I get that type in there right, then all I have to do is copy it down here. Hopefully it's correct. And then v of n, the new v. I use the old v up here. I think ideally, to get the best result, I'd use the average between the old v and the new v, but I didn't have the new v yet. I wasn't going to get the new v until I used this, which depended on the new x. That's why I used the old v, and I'm calculating the new v now. So the new v is equal to the old v plus the acceleration. I use the current acceleration times the time step, the amount of time dt. So the old v plus the change in v during that time interval. And I think that's it. I'm going to hit a carriage return that wasn't called for. Let's try that. Or let's take a look at that. Let's check on that. So Tn is equal to n minus 1 times dt. I had a mistake in my pencil and paper. And then and then the xn is x sub n minus 1 plus the old v times the time step. Okay. The acceleration is that. I think I want to try to take a quick look at the acceleration and make sure that that checks. And I'll divide by the mass times all that to the 3 halves. And then all that is x sub n minus x1 quantity squared plus y1 quantity squared. Let's see. I think it looks good. Alright, so that's all we do in the while loop, and then we gotta plot these guys. So I gotta divide up the page into 3 regions. Go subplot 3 rows, 1 column, start off with the first element. That would be in there. We plot it's supposed to be x versus t, so we go t comma x. Here the semicolon, it's used to make it so that the computer doesn't print the value that got calculated in that step to the screen. It's not really needed for subplot and plot, but just to be consistent, I choose to put it on there. And then I'm going to try copying those two lines. Control C, Control V, paste them twice. 3x1, region number 2, 3x1, region number 3. Here I'll plot V, here I'll plot A. I got a line open there. I think I'll go ahead and do my comment and advanced percent attribution. And I guess I'll just get started with that. So up here, get to thinking a little bit about that. I'm afraid I'm going to forget to put my name on there. So I go percent by Jeffrey Schneck. We got a lot more documentation to do, but I'll pop a little bit in there while I'm thinking of it. So let's try saving this. I'm supposed to use the file name motiongraphs.m. Save motiongraphs.m. And let's see what happens if I try running motiongraphs.m. It takes arguments. It was the mass. Let's try 0.005 kilograms. Oh, cool. As I start to type it in, it tells me what it takes. It takes the charge and the velocity. I'm going to go comma 1.5 times 10 to the minus 6 for the charge. Just making up some numbers. The user gets to use this function with whatever set of 3 values they want. And I remember talking about it before. I'm going to call that 100. So getting something that looks kind of choppy here, and I think I'm going to try some more points. So close that window, and I gotta play around with the points here, so I'm actually going to temporarily make it easier to change how many points I use. So it's the time step. If I make that smaller, it's going to take more time, use more time values. So I'm going to put time step dt up here as an argument. In the end, it can't be there because then it wouldn't meet the project requirements. It's only supposed to have 3 arguments, but I can do that temporarily. And I'll put a % sign in here, and after I figure out what works well, I'll change this value to that and then make that not be an argument. But for the time being, that's what I want to do. So I gotta type in what the time step is going to be. It seemed to work, so tend to start off with kind of a big time step, and then if it turns out to be working, then I can try it with a small time step. So I mean, when I say it was working, the program ran. Alright, so here's what we got. This is position versus time. I do have to label those graphs. Velocity versus time, and acceleration versus time. So it seems to only be moving forward. With the velocity, it's slowing down, and then it gets to around 1 times 10 to the minus 3 meters, and starts speeding up. I would expect where things kind of went funny, and then it goes to 2 times 10 to the minus 3. I'm expecting this to go from 0 to 0.2 not 0 to 0.002. So I think I better take a look. I want to make sure that's what's going on. I'm going to try checking values. So it's saying x is 0.2 there, and I wanted it to go all the way out to 0.2. So let's see if I typed in something wrong in the editor. I think I can keep that picture there. Go to the editor. So it's this one. And yeah, I would accept it to say, well, it's less than 0.2. Well, x is less than 0.2. So I would expect x to be a lot bigger than 2 times 10 to the minus 3. It's just 2 times 10 to the minus 1. So take another look at the picture there. It's saying it's 2 times 10 to the minus 3 at that point. And then where things are switching around, it's about 1 times 10 to the minus 3. So we got something wrong there. I got to do a little bit of debugging to find out why that's such a small value there. So to debug it, the usual process is to make it print stuff out. So I'll go to the editor, and I'll make it print out the values of x. But if we run it like that, it's going to print out a lot of values of x. So at the same time, I use a smaller step size for the time. Is like 0.01. And let's see what happens. X is equal to 0 and 1. That's too small a step size, probably, or too big a step size. So it goes 0.1, 0.2, and then 0.3. And if I go even bigger step size, then it goes, looks like the last time x got printed, it went from 0 up to just barely over 0.2. So the values of x appear to be correct, and yet what's being plotted is not correct. So let's take a look at what I've got in there. I'm going to try. Okay, my mistake was I was mistaking the time value for x. So the values of x are on the vertical axis in the graph, just misinterpreting the graph. And they're supposed to go from 0 to 0.2. That looks good. So these are time values. So what it's saying with the charged particle that I got, it doesn't take very much time. So sorry about that. Just a mistake on the interpretation of the graph. So x is going to be along here. It does go from 0 to 0.2. That looks perfect. And these are time values, not x values. Alright, so we can make it so that next time I run it, it doesn't print that value of x. Some unnecessary debugging there. And I'll save that. And I do want to use remember to use a smaller time step. Actually, let's go ahead and run it again with a small time step. I'm going to close out the graph window, go to the command window, up arrow, and I'll try 1, 2, 3 of those. Let it run. And it is looking good. So let's see what we can see. As time elapses, this thing getting higher on the graph, so it's moving forward. What happens to the speed? Initially, it's moving along pretty constant, but apparently gradually decreasing here. At this time, looks like about 1.1 times 10 to the minus 3 seconds. It must have gotten to our set of 4 charged particles. You know, the position on the x-axis, all 4 of those are a little bit off the x-axis. My victim, whose motion we're graphing here, is on the x-axis. But that's where it passes the set of charges. And now it's past these positive charges. It's positive itself, so it's being repelled from them always. But now it's being repelled in the same direction it's going. Here, it was being repelled backwards. It was being slowed down because the charged particles, those fixed charged particles, are ahead of it. Here it passes them, they're behind it now, so they're pushing it along, so it speeds up again. So the velocity makes sense. The acceleration, relatively small, out there pretty far away from the charged particles where we start, and then as time elapses we're getting closer and closer, and the acceleration is going negative. And then right here, where I got the cursor, at that particular instant in time, again it looks like 1.1 seconds, so it's consistent with the graph out there. The particle is right at those charged particles, so you know, one's above it, one's to the right, one's to the left, one's below it. But the forces that they're exerting on it are canceling out. There's no x component to the total force, which, given that the total force is 0 anyway, and then it passes that, and now it's getting pushed in the forward direction. We got a positive acceleration, so that's actually looking perfect. This seems to be working very well. I think I want to blow up the velocity graph. Actually, look at the values. From conservation of energy, when we start, we're the same distance away from the particle as we are at the very end. You know, we started out at 0, wind up at 0.2 meters, and the charge distribution is that x is equal to 0.1 meters, so it's the halfway point. So given that we're the same distance away, that means we should have the same electrostatic potential energy, and given that no energy has been delivered to the outside world or transferred in from the outside world, the total energy should be the same. So if the potential energy is the same at these 2 points, this one and this one, then the kinetic energy should be the same, which means that the speed of the particle should be the same at those 2 points. So I'm going to click up here to investigate it. Click on a point on the graph, and then I can move that around. So it starts out at 100 meters per second and winds up at 100 meters per second. So note that we're making a little approximation with every time step, that the velocity doesn't change during the time step and the acceleration doesn't change during the time step, which isn't true. It changes a little bit, but we've used very tiny time steps, and even with tiny time steps you might expect there to be a little bit of error in each step, and those errors could add up. But this is an indication that they're not adding up enough to make a difference. So this is very encouraging that the velocity is exactly like that. In fact, it should be symmetrical any point a certain distance to the right of the position where the charged particles are. So this is where it's on here. This is the time at which it's at that position, and the motion should be symmetric, and so at a corresponding time to the left we should have the exact same value. And in other words, the whole graph should look very symmetric, and it does. Plus we were able to make sense of this. I do want to play around with I want to make one more check here. So the conservation of energy check is a pretty powerful check there, and really gives me a lot of confidence that this is good. We don't need to use a smaller time step, for instance. But if the particle starts out slowly enough, then it shouldn't make it. It'll be slowed down so much that it comes back. So this graph, at the end of it, whatever time it gets to at the end, it should be 0. So it should go up and then down, goes forward and then comes back. So in the case that I've investigated here, it just keeps on going forward. So it's being slowed down as it approaches the distribution of charge, and then it gets pushed along. It's being sped up as once it gets past it. But it never gets slowed down to 0. So let's see if we reduce the speed here. Oops, what I'll do, up arrow, and then I can edit it. I'll try just cutting it in half. Well, let's go to 10%. I'll just keep dividing by 10 until we get a difference. You know what, this is taking a little bit long to run. I'm going to try to take out one of those zeros. We'll use a bigger time step next time. In fact, I'm getting impatient, so I'm going to hit Control-C, which should stop it, and it does. And I'll try that. I'm going to take out 2 zeros, 1, 2, and let's see if we're getting the same results that we got before when we were running with 100. So it goes a lot faster, and I want to look at the velocity graph. It looks a little bit funny at the end there, so maybe. No, I think that's just the resolution of the screen. So let's try looking at it again, the conservation of energy check here. So I was using 100 times as many points as I needed. At least I might not need as many as I've got, but it's already running fast enough, so I don't think I have to go any smaller. But I do want to try this smaller. Let's see. So I got it moving relatively slowly now. And it goes, the program runs quickly, and we get looks like the results that we expected. So I want to check actual values. So verify that I started at 0, and then in the end, very, very close to 0. Minus 6 times 10 to the minus 5th. So it went a little bit past it, just because the time step is not infinitesimal. Let's see if the velocity graph makes sense. It's got a little curvature to it. It's curved up over here and curved down here, associated with the fact that the acceleration is changing. But it does go through 0 at the same position where the position peaks. The acceleration here, it's negative to start with, and it's always negative. So we're always below minus 2500. So it's always being accelerated in the backward direction. So it's pretty clear. It goes forward, forward, forward. It gets doesn't get very far at all. Doesn't get very far at all, and then turns around. So let's launch it a little bit faster. I'm going to actually try 50. See what it looks like. Alright, still doesn't make it past the distribution of charge, but now it's more obvious. We can see the curvature there. The velocity does go through 0 as it gets as far as it goes. Look at that, it almost makes it to the charge distribution. So almost makes it, but it comes back. So the acceleration is always negative. You see the top value is 0 there, and then it's got negative values. When it gets close to the thing, the acceleration is greater in magnitude, so more negative. So I think it's making sense on that part too, that if you don't give it enough initial velocity, it's not going to make it. Just to play around with it a little bit. I want to see where, if I'm guessing it makes it through at 60, because this came so close. Nope, it still comes back. You know, with this combination of mass and charge, one, you know, could use this code to find out, you know, how fast does it have to be going to make it through. You run this more times than I'm going to, but I think it's going to be somewhere between 60 and 70. It's with an initial launch speed of 70 meters per second, it makes it through, but with 60 it didn't. So here, you know, it just keeps on going forward. The velocity is very close to 0. But it's still a positive velocity where as it passes through the charge distribution. Let's make sure that our check, conservation of energy check, still works. 70 to 70.04. So it's drift off a little bit. It's it seems a little more sensitive to the step size when we're there. I think maybe I'll make that, you know, when we're close to that turnaround. Close to that velocity at which it would turn around, but slightly above it. So let's see if it still goes reasonably fast if I use a smaller time step. Yeah, so it's done in a jiffy, and yeah, that's right at 70. So conservation of energy check. It checks out to the number of sig figs that we're using in the display here. So I think I'm going to use that as a time step. So before I close the video, remember we have to change that just because of the way it was stipulated in the project handout. So in other words, I hardwire in that time step as opposed to making it a variable, an input variable that the user gets to use. That's a control V I use to put it in there. I'm going to take away the comment symbol, so now it's actually going to be used, and I take it out of the argument list and try running it again, but without providing that argument. I should get an error if I do include the argument. And yeah, it's still working just fine. So I'm going to call that, and take one more look at the graph. I was trying to bring it down here so you can see the whole thing. I'm going to call that a wrap on this video. So the next, well, I just said a wrap and I keep on talking. The next one, I do documentation and finishing touches. So we got to title the graphs and title the axes of the graphs, and include all of the documentation that it said to in the project handout. All right, that's it.